to further the subject of confidence intervals, we're going to take a look at what we call z-critical values. Remember that we use z generally when we're talking about normal distributions. So looking at this bell-shaped curve here, we saw early in the course that the 95% rule states that 95% of the values approximately are within about 2 standard deviations of the mean in any bell-shaped curve. If that distribution is exactly normal, then we can get a little more specific than 2 standard deviations of the mean. We can see from this picture here that if that's the center 95%, it looks like we go from negative 1.96 to positive 1.96, which means that 95% of the values are within 1.96 standard deviations of the mean. And we call that 1.96 a z-critical value, which we often refer to as z-star, because rather than being a z-score from a particular calculation, it's a critical cutoff value. We call it z-star for 95%. So looking at these two curves down here, we can see that the first one seems to correspond to a 90% confidence interval because we have the center 90%, and that our critical value is 1.645. Then when we look at 99%, we can see that it looks like everything is within 2.575 standard deviations of the mean, and therefore for a 99% confidence level, we would have a z-star critical value of 2.575. Now, just a minor little note, you will find more frequently the value 2.576 showing up in tables. For whatever reason, StatKey with its rounding just was giving me 2.575 for this particular question. So the way that these z-star critical values are used is to allow us to find confidence intervals for confidence levels other than 95%, still using an estimate of standard error instead of using that percentiles method. This is what's going to free us from the bootstrap distribution. So if we recall in Chapter 3, when talking about bootstrap confidence intervals, we had a formula for margin of error that was 2 times the standard error, provided that the sampling distribution is approximately bell-shaped. Now we can generalize that and say it's not always going to be 2 that we use here. We're going to fill in whatever the critical value is and say not just an approximately bell-shaped, but an approximately normal sampling distribution. And so instead of 2 times the standard error, we now have that the margin of error is z-star times the standard error. And therefore that gives us a formula for a confidence interval when we take into account that our general formula said sample statistic, which is always going to be p hat if we're talking about a confidence interval for one proportion. So we have a sample statistic plus or minus a margin of error. So it really isn't new, it's just a slight variation on something that we're already pretty familiar with. So let's look at an example. We have sleep position. There's an exercise in the textbook that describes the details behind the study, but we have all the information we need right here to at least calculate the confidence interval. We had 1,000 adults in the sample, and the proportion of that sample that sleep in the fetal position, or at least that start out sleeping in the fetal position, is 0.41. And we're given an estimate of the standard error, so this is my SE right here, 0.016. We want to find a 90% confidence interval for the proportion of all adults in the UK who start in this position. Oh, well, I have this statement twice, so let's just ignore the second statement here. All right, so what we want to do is first find the margin of error. The margin of error is Z star times the standard error, and Z star only depends on the confidence level. We want a 90% confidence interval, and we just established that Z star for a 90% confidence interval is 1.645. Therefore, my margin of error is equal to 1.645 times this 0.016. And we can bring in our calculator now to do this quick computation. And get 0.02632. I'll think about how much rounding we want in that in the next step. So my confidence interval is p hat plus or minus my margin of error. My p hat is to 2 decimal places, and I would say the margin of error, often you want to either match the decimal places of your statistic or take it one further. In this case, it's kind of a judgment call. If I match, I've got to round that all the way to 3%, which seems like it might be just a little too much rounding, so I'm going to go ahead and take it all the way to 0.026. And then I can bring in my calculator again, subtracting to find the lower bound and adding to find the upper bound. So 0.41 minus 0.026 gets me 0.384. And 0.41 plus 0.026 gets me 0.436. So it looks like what we can conclude from this is that in the UK, somewhere between about 38.4 and 43.6% of adults start in the fetal position when they go to sleep. Now we're also given a formula for standard error, and this looks a lot like the formula we have for standard error for a hypothesis test. The only difference is now everything is based on p hat instead of p naught. There is no p naught in a confidence interval context, right? So it's p hat instead of p naught. Otherwise, it's the same formula that we have for hypothesis tests. So let's go ahead and verify that standard error estimate that we were given. This should be standard error equals square root of my p hat we decided was 0.41. 1 minus that 0.41 is 0.59. And then I'm going to divide by n, which is 1,000. And I want to make sure the whole thing is clearly in the square root, not just the numerator. So that in my calculator, the expression I'm going to enter is 0.41 times 0.59, then divide by 1,000, then hit the square root, because this particular calculator just takes the square root of whatever is on the screen. The order in which you enter these might vary from one calculator to another, especially if you have a higher end calculator. It's going to let you put in the whole expression. But usually those are the calculators where people need less help. All right, so we get a standard error of 0.01555. And we can see ours was rounded to 3 decimal places. So rounding here, since the next digit is a 5, we would round that to 0.016. So now we can see that we could find a confidence interval even without being given a prior estimate on the standard error, if all we know is the sample proportion and the sample size.